Hey guys, it's Jamie here. So today we're going to go on to Aircraft Systems and Performance 2, Episode 2. So number 1 we're going to go through is the definitions of airspeed. Number 2, equations regarding a turbojet and a propeller aeroplane. Number 3, stall speed. Number 4, required thrust and minimum speed. And number 5, minimum drag speed and minimum power speed. So it was made very clear that the true airspeed will be used rather than the equivalent airspeed, and I'll explain why in a minute. So, the definitions of airspeed. Number 1. So, we're told that the equivalent airspeed is equal to the square root of the relative density multiplied by the true airspeed. Relative density is equal to rho over rho naught. Our density in flight and our reference density. So in order to use the relationship, we need to use the actual density used in flight, which is very difficult to determine. Therefore, it's much easier to use the true airspeed, which is determined using a pitot tube. So number 2 was the equations for a turbojet and a propeller aeroplane. So the nomenclature we are about to use: T is equal to engine thrust, D is total drag, M is total mass, L is total lift generated, R is the total reaction force, U will be the velocity along the x-axis, and W will be the velocity along the z-axis. Theta will be the pitch rotation, and mu will be the coefficient of friction. So, as you can see in my little attempt of an aeroplane, thrust is going to the left, lift is going upwards, drag is going to the right, weight is acting downwards, as usual, hopefully, and we have our reaction forces acting upwards. So this is for a turbojet, and the equation that governs the turbojet is T is equal to d plus mg sine theta plus dm by dt multiplied by u plus du by dt multiplied by m plus mu times r. So because it's the thrust, we've resolved in the x-axis. So T is going to be equal to the drag force plus all the other forces acting against the thrust. So the drag, the weight component in the direction of the x-axis. So we use sine theta, so mg sine theta. This value here is the acceleration. However, it's due to a change in mass, which can occur from dropping weapons or supplies, not due to a change in speed. Our next value here is simply the momentum. So we know that momentum is the rate of change of velocity, and then, it's the force due to momentum. And then finally, we have mu r, which is the runway friction, mu our coefficient of friction, r our reaction forces. Moving swiftly on, here we have the lift equation for the turbojet, which we've now resolved in the z direction. We don't have drag here because there is no drag acting in the z direction. We just have the weight, which is mg cos theta, because we have to take into account the pitching of the aircraft. We then have the acceleration, similar to the one before, change in mass multiplied by our z velocity divided by the change in time. Then we have our force due to momentum, and finally, acting against that is our reaction force. And the only thing we need to do to change it for the propeller aeroplane, the thrust is the same as the turbojet. However, because the thrust for a propeller aeroplane is equal to eta p over v, where v is our forward velocity eta is our propulsive efficiency, and P is our engine power, we can just equal that to our equation on the top, and we have our equation for a propeller aeroplane. Number 3 is pretty straightforward. Aircraft is flying at its lowest speed where lift is equal to weight. So L is equal to W, lift is equal to weight, which is equal to half rho v squared, rho being the air density, v being the stall speed, S our wing area, multiplied by our CL max. The reason why we use CL max rather than any other CL value is because the angle of attack is at its maximum at stall speed. So then we can rearrange all this to get our stall speed, which is the square root of 2 times by the weight, all over rho S CL max. Number 4, the required thrust and maximum speed. First we have to look at it at cruise, and at cruise the thrust is going to be equal to the drag. So the thrust is equal to half rho v squared S CD, CD being our coefficient of drag. And our coefficient of drag at low speeds, so subsonic speeds, is going to be equal to CD naught plus K over pi A CL squared. Now CD naught is our profile drag. Our K over pi A multiplied by CL squared is our induced drag, where K is the induced drag coefficient, pi is pi, and A is the aspect ratio, which we'll know is the wingspan squared divided by the wing area. Oh, so you know what our coefficient of lift is. So we put our coefficient of drag back into the thrust equation, and we get this. Now we also know that lift is equal to half rho v squared SCL. Rearrange to find CL and square it. So then we have W over half rho v squared S, all squared. Put that back into our thrust equation, and we get our final equation. That's this big bad boy. Now this, we can iterate to find our maximum velocity at maximum thrust. And finally, if we want to use this equation for the propeller aeroplane, we know that thrust is equal to eta P over V, which then we know is equal to all of that, which we put there. Multiply by V, and we get eta P half rho V cubed S multiplied by all of that. We can then use that and iterate again to find our maximum velocity at maximum thrust. And finally we have minimum drag speed and minimum power speed. So on our y-axis we've got drag, x-axis we've got velocity. First one we can draw is like this, which is v squared. This is our profile drag. This increases, the drag increases with velocity here, whereas for our induced drag, it actually decreases with velocity. Now the reason this happens is because the induced drag is dependent on the coefficient of lift, and we know that the coefficient of lift depends on the angle of attack. So the slower the aircraft is moving, the higher the angle of attack is, therefore the higher the coefficient of lift is, and therefore at our lower velocity the induced drag is at its highest. And so if we wanted to find our total drag, we'd use this line here, where this point here is our minimum drag. And if you wanted to find the total drag, you can add together the profile drag and the induced drag. And finally, one last thing. This table is of paramount importance. It will be in your notes, so don't worry if you don't understand or can't read what I've written. But this table, we are expected to remember it all, And if you're unsure what B and A are, A is the coefficient of drag naught, so that's the profile drag, and B is K over pi A, K being the induced drag factor, and A being the aspect ratio. So that's all I have for you guys today. If you have any questions or queries, please leave a comment in the description below. If I've done anything wrong you feel I need to correct, please let me know. Otherwise, don't forget to like and subscribe. I'll see you guys next time. Bye!